In chapter 12, we defined climate, and we talked about how we can tell one climate from another. So now we're going to move here into chapter 13, discussing how the climate can change from time to time. In this video, we'll start off by talking about how we get data that tell us about the past climate. How can we reconstruct the past? There are multiple methods for reconstructing past climates. There are some of the common ones are listed here. We can easily tell from glacial landscapes. As a glacier melts, it carves out land, quite literally. Those are great big, huge, they're mountains of ice. So as they melt and they push down, they can actually carve out some of the land. So geography tells us a lot about what the glaciers were like thousands of years ago. Here's another simple one called CliMap. What they do is they go down to the bottom of the ocean floor and they dig down and they keep things ordered, and they dig down, oh, say a couple hundred meters or more, maybe even a kilometer, and they just take a sample of some of the sediments that have settled at the bottom of the ocean. You have dead plant life, you have shells, fossils, as well as other particulates that are down in the ocean floor that, when you analyze their chemical makeup, tell us a lot about what the atmosphere was actually like hundreds of years ago. Very similar to CliMap, instead of digging for a core of dirt from the bottom of the ocean floor, is digging for a core of ice in the bottom of a glacier, very common in Antarctica and in Greenland. Well, what good is this? Well, inside of the ice, there are little pockets of air that are trapped. When you extract that air, you can actually measure how many, the different oxygen isotopes in that air. Now, an isotope is just a molecule with a different number of neutrons. Excuse me, not a molecule, an atom with a different number of neutrons. In this case, oxygen. Typically, we have oxygen 16, which would be oxygen atom with 18 protons plus 18 neutrons. But every once in a while, you get what's called oxygen 18, which would be 8 protons plus 10 neutrons. And that ratio tells us a lot about precipitation, tells us a lot about temperature, it just tells us a lot about life and the atmosphere in general, from however many years ago that oxygen was trapped there. And based on the decay rate of these oxygen isotopes, we can tell how old that air really was. So all three of these can tell us what happened thousands of years ago. Something on a shorter scale would be dendrochronology, dendro meaning plant, chronology time. Basically, we're looking at the growth of tree rings. Every year, the tree forms a new skin, basically the bark of the tree, and the old bark gets morphed into the wood of the interior of the tree itself. And so you can tell how much precipitation was in a given year, because if you have a lot of precipitation, there's a lot of growth, so you have a really thick ring for that year. If it was a dry year, the growth of a tree ring for that year is rather short as well. So after reconstructing through the climate through those methods and many, many other methods as well, we have found out that the most recent ice age actually reached its peak, between 18 and 22,000 years ago, where the Earth was actually only 4 to 10 degrees Celsius cooler than it is today. That doesn't seem like much. I mean, we can go through that temperature change in a day. But when you're talking about global average temperatures, it makes a huge difference, a very large difference. So that was the Earth's average temperature 18 to 22,000 years ago. So, and that was the peak of the Ice Age. we started coming out of that ice age about 11,000 years ago, and we've been coming out of it since. In fact, one could say that we're still coming out of that ice age. Here are some diagrams showing what the Earth may have been like 18,000 years ago at the peak of the last ice age, and how much of North America and Europe was actually covered in ice. And yes, it's a fair amount. So what's happened since then? Well, temperatures have been increasing since then. Now, we have made a big deal about the most recent increase in temperatures. But this is not the first time it's happened on the Earth. If you notice here, 18,000 years ago, we were in our peak of our ice age. And then roughly 13,000 years ago, bam, we had a sudden increase. Maybe not quite as sudden as what we have today, but it is a sudden increase. So you have a sudden warm period. And it cooled down, went back the other direction, had an unusually cold period. We call this the Younger Dryas period. And so this is kind of like a mini ice age that happened over about 1,000 years. And then, sure enough, what happened? You have an increase in temperature just about as drastic as the one that we're experiencing right now. And then since then, we've kind of hovered around this dotted line, which is the normal temperature from the last 30 years, 100 years, whatever they use to calculate that average. But yes, we've kind of hovered over there, around there for the last 10,000 years. Yeah, between 4 and 7,000 years ago, we experienced what's called the Holocene maximum, where sure enough the Earth was much, much hotter than it is even today. And what else can we see? We can also determine changes in ocean currents because of glaciers and cooler waters, difference in weather patterns. It changes the ocean currents. So where 18,000 years ago, the ocean current pretty much cut straight across the Atlantic towards Spain and then cut up northward towards Great Britain and Ireland. Now, they sort of do the same, but they go further north and they pick up more warm water. And you can notice how these warm water temperatures have expanded into other regions. So yes, definitely today, the oceans have definitely felt a huge difference in temperature from what they did 18,000 years ago.